everyone. Today we are going to discuss amplitude modulation, demodulation in detail. In last lecture we have covered amplitude modulation, that we will revise that portion in this lecture also, and then we will come to the amplitude demodulation. The subject communication engineering KC 401. Once again, what is modulation? Then modulation, basically it is the process by which some characteristics of the carrier signal is varied in accordance with the modulating signal. There is already a modulating signal which is to be transmitted from source to destination, and there is a carrier. In that carrier some characteristics of the carrier is varied in accordance with the modulating signal, basically amplitude of the modulating signal. Then if you vary the amplitude of the carrier as per the amplitude of the modulating signal, then it is the amplitude modulation, and if we vary the frequency of the carrier signal as per the amplitude of the modulating signal, then it is the frequency modulation, and if you are varying the phase of the carrier signal as per the amplitude of the modulating signal, then it is the phase modulation. Okay. Then these are the continuous wave modulation. Okay. What are the need for modulation? See, actually the modulating signal is a low frequency signal, okay, and for low frequency signal to transmit from one place to another place or source to destination, we require basically the antenna with the length of lambda by 2, lambda by 4 like that, and then lambda should be very small. For lambda to be small, the frequency should be high, but modulating signal because having a low frequency, signal, so that its lambda may be higher than the antenna length, that is lambda by 2 or lambda by 4, that may be higher, okay. And that because a modulating signal may be in the kilohertz, then lambda may be in the kilometers, then that is not possible. Then we require modulation with a carrier signal, so that suppose we are increasing its frequency, okay, the carrier is a high frequency signal, then its wavelength lambda very low, okay. Corresponding antenna length, the practical length of antenna becomes comes in the meters, then that is the feasible, that is the possible, okay. Similarly, other need for the modulation, that is the narrow banding of the modulating signal, okay. See, because modulating the wave the bandwidth of the modulating signal is low, okay, and the frequency of the carrier signal is high, then in comparison to the frequency of the carrier signal, its bandwidth is very low, then it is basically making a narrow band at that corresponding, suppose this is the carrier frequency f c, okay, and this is the bandwidth of the modulating signal, then when it comes around that f c, okay, then it is making a narrow banding signal, okay, and then it is possible, it is easy to transmit the narrow band signal, okay, in comparison to the wide band signal, okay. Next, frequency multiplexing. See, by at different carriers, carrier frequency f c 1, f c 2, f c 3 and so on, we can put multiple modulating signal at different the carrier with the different frequencies. Suppose that is this is the f c 1, okay, and similarly another signal with the same bandwidth can be put at the f c 2, f c 3 and so on, okay. Then frequency multiplexing also possible, okay, when we are using the high frequency carrier, okay. And effective power radiated by antenna, because the power is directly proportional to 1 upon lambda square, okay. So when lambda is low, okay, corresponding like that it is proportional to lambda in that case, okay, then low power or effective power can be radiated with the low wavelength of the signal or high frequency. Then high frequency signals require low power to be radiated. Okay. Then these are the some needs for the modulation. Types of modulation, then modulation basically two types, analog modulation and digital modulation. Here we will use the continuous wave with some high frequency carrier. Okay. Here also we will use some carrier, okay, but that carrier carry basically the digital signal. When modulating signal is sampling, quantizing and encoding, then after encoding that binary signal can be transmitted through that carrier in the digital modulation. In analog modulation, that analog signal directly can be the carrier can be modulated as per the analog signal. Okay. Then it is the analog modulation. Analog modulation, it is of three type: amplitude modulation, frequency modulation, phase modulation. Okay. As we have discussed that when amplitude of the modulating signal, okay, is used to modulate the amplitude of the carrier, then it is the amplitude modulation. When frequency of the carrier is varied as per the amplitude of the modulating signal, then frequency modulation. When the phase of the carrier signal is varied as per the amplitude of the modulating signal, then phase modulation. Okay. Here in digital modulation, basically amplitude shift keying, frequency shift keying and phase shift keying. Okay. Then here the carrier is used, suppose we are transmitting 0 1, okay. Then for 0 1, for 0 there is a no signal, for 1 there is a sine wave or cos wave with some amplitude can be transmitted with the fixed frequency, constant frequency. Okay. In frequency shift keying, basically the for 0 1 suppose, then for 0 1 carrier signal, sinusoidal carrier signal with other frequency, and for 1 another carrier frequency transmitted for 1. Okay. Then FC1, FC2 like that. And in phase, basically we vary the phase of the carrier signal for 0 and for 1 like that. Okay. That is the binary modulation. In case for quaternary and octernary, we will corresponding change the amplitude labels, frequency and corresponding the phase. Okay. Then these are the type of the modulation. Now come to the amplitude modulation, that is the main topic here to be discussed. Then amplitude modulation is defined as a process in which the amplitude of the carrier wave is varied about a mean value linearly with the baseband signal MT. Okay. Let message signal is the MT in time domain, and carrier wave can be given as the sinusoidal waveform Ct is equal to AC cos 2 pi FCT, that is with the frequency Fc. Then amplitude modulated waveform can be given by this equation, St is equal to AC 1 plus Ka Mt cos 2 pi FCT. Basically this is nothing but the AC cos 2 pi FCT plus AC Ka Mt into cos 2 pi FCT. Then we transmit a carrier signal, okay, because Ct is AC cos 2 pi FCT. Then we are transmitting a carrier signal along with this modulated signal in when we are transmitting St. Okay. And here K, that is the coefficient, it is a amplitude sensitivity, as well as this Ka Mt, okay, Ka Mt when we are taking its mod value, okay, this is nothing but the Ka am, suppose am is the maximum of the modulating signal. Okay. Then this part is also known as the modulation index mu. Okay. It is the modulation index. Okay. That we will see in the next slides how we can use. Okay. Now, the waveforms for the amplitude modulation. Okay. This is the basically modulating signal MT, okay, which is the main original signal. Okay. Suppose audio signal or video signal like that with a limited bandwidth. Okay. And it is the carrier signal CT. It is a high frequency signal, but obvious. Okay. And here this in this carrier we have to vary the amplitude of the carrier signal as per the modulating signal or as per the amplitude of the modulating signal. Okay. Then this is the waveform ST as is given in the last slides in terms of equations. Okay. Then ST is nothing but the that is AC 1 plus k mt cos 2 pi FCT. Okay. Then this ST when this is nothing but the ST is nothing but the AC 1 plus k mt into cos 2 pi FCT. Then firstly we will generate 1 plus k mt, then multiplied with this 1 plus k mt with the CT, that is the AC cos 2 pi FCT, then we will get this signal. Okay. Okay. When we generate 1 plus k a mt, okay, and then multiplied with the CT, then we will get this amplitude modulated waveform in this way. Okay. At the envelope of this waveform we are getting the similar as per the modulating signal. Okay. And its negative version also possible. Okay. Now, next, the essential requirements for amplitude modulation, then that is KAMT mod, that is nothing but the modulation index mu. The modulation index mu, it should be less than 1, it should be less than 1 for all t. Okay. And other requirement, that is the carrier frequency Fc, carrier frequency Fc, that is the frequency of the carrier signal CT, then this Fc should be greater than the bandwidth of the message signal or highest frequency component of the message signal. Whatever message signal, it have some highest frequency signal, highest frequency component, then the Fc, the frequency of the carrier signal should be much higher than the highest frequency component of the message signal. Okay. This is the requirement, because if Fc is not too much high than W, then we will not get the envelope correctly, okay, as in the last slide. Next, amplitude modulation, then modulation index given as mod of kmt, that is the mu. Okay. And here we can see that suppose this is the MT signal, this is the modulating signal. Okay. And in this figure when kmt, that is the modulation index less than 1, when it is less than 1, then you are getting amplitude modulated signal in this way. Okay. When modulation index equals to 1, then that this lower end will touch to its base, that is the 0. Okay. And when modulation index mu, that is the mod of kmt, greater than 1, then this lowest part, it becomes negative and goes inside this one, like that, this one, in this one, this one. Okay. And its negative version, it crosses this baseline. Okay. So that here we get some phase reversals and distortions when we are demodulating its envelope to get the message signal MT. then we will get some distortions here. Okay. Then to remove those distortions, okay, in amplitude demodulation or detection, the modulation index should be less than 1, even the critical point when modulation index equals to 1. Okay. Here one more thing, the calculation of the modulation index mu, that can be, suppose this is the V max and this point corresponding, that may be, that is the V min. Okay. Okay. Then V max, that is the maximum of, suppose S t is given as AC 1 plus KMT cos 2 pi f c t. Okay. Then V max is the maximum of the S t. Okay. V max is the maximum of the S t. Then you will get the value AC 1 plus K or maximum of M t, suppose A m. Okay. This is the V max, and V min, this is nothing but the minimum value of S t positive. Then AC 1 M t, its maximum is the A m, minimum may be minus A m, then 1 minus K A A m, this is the V minimum. Then we can find K A A m, that is K A A m, that is nothing but the modulation index mu equals to V max minus V min divided by V max plus V min, that we have already discussed in the last lecture also. Okay. Then this is the formula can be used to find modulation index experimentally when you are finding it. Okay. Now, amplitude modulation in frequency domain. Okay. Then as equation suggests, ST that is the AC cos 2 pi f c t plus AC K A M t cos 2 pi f c t. Okay. When this time domain signal converted into the frequency domain signal, or we are taking its Fourier transform, then this time domain signal converted into the frequency domain signal, then SF and then AC cos 2 pi f c t, its frequency version AC by 2, its delta f minus f c plus delta f plus f c, and this one AC k m t, then AC k m t, then AC k a m t into cos 2 pi f c t, then m t into cos 2 pi f c t, then m t corresponding to m t there is a its Fourier transform m f, then m f shifted at the frequency f c, then its m f minus f c as well as m f plus f c, that is the minus f c. Okay. Similar, that we are getting delta f minus f c plus delta f plus f c, we are getting here m f minus f c plus m f plus f c. Okay. Then this is the frequency domain signal of the amplitude modulated signal. Okay. Then this is the Fourier transform corresponding to the m t, and here we can see that m f, that is the frequency domain signal of the m t, here its highest frequency component is W. Okay. And its negative in negative frequency we can see it minus W to 0. Okay. Okay. Then this is the Fourier transform of the m t, and this is corresponding to Fourier transform of S f, we can draw in frequency domain. Okay. Then here we can see delta AC by 2 amplitude delta f minus f c, that is the delta f signal at f is equal to f c, then AC by 2 delta f minus f c, one component. Second, AC by 2 delta f plus f c at minus f c. up to this amplitude, this one. Okay. Here K AC by 2 with this amplitude K A AC by 2, okay, M F minus F C, then this M F can be placed at F is equal to F C, then it is 0 shifted at F is equal to F C, okay, here this one, okay, similar. And similarly, the same M F can be shifted at F is equal to minus F C here, corresponding to this M F plus F C with amplitude 1 upon 2 K A S C, okay, like that this one, okay, and M 0 basically at the frequency 0 whatever amplitude that is shown here, okay, that is the this M 0, okay. Now, this is similar to this one, this is also similar to this one, but place changes at F C and at minus F C, okay. Here we can see in M F also, this is the upper sideband, okay, upper sideband, and in this is the lower sideband, okay, in M F, and same now it is shifted at F is equal to F C and F is equal to minus F C, then this part upper sideband and this part lower sideband. Similarly, here at F is equal to minus F C, this part, okay, because this is nothing but the mirror image of this signal, okay, then this is nothing but the, this becomes the lower sideband, okay, corresponding to this one, and corresponding to this it is the upper sideband, okay. Then this is the spectrum of the baseband signal and the spectrum of the AM wave. Now, limitations of the amplitude modulation, then because we know that ST is nothing but AC cos 2 pi FCT plus KA AC MT cos 2 pi FCT, then we are transmitting AC cos 2 pi FCT along with this modulating signal, okay. Then there is a no need to transmit this signal because it is independent with the modulating signal MT. Then when we are transmitting ST along with this, then it is nothing but the wasteful of the power, okay. Okay. We should transmit only this part because here MT along with the carrier signal CT, okay. Then this power wastage of power can be reduced, okay, as well as it is a wasteful of bandwidth because in this figure here this upper sideband, its mirror image is the lower sideband, then it is nothing but the similar as the upper sideband, only its mirror image, okay. Then there is a no need to transmit both sideband, upper sideband as well as the lower sideband. We can transmit either upper sideband or lower sideband, okay, so that the requirement of the bandwidth could be reduced to half, okay. Then if you are transmitting in this way, then it is nothing but the wasteful of the bandwidth. Then bandwidth wastage also can be reduced if you are transmitting only upper sideband or lower sideband. Here because this we have already, okay. Now come to the next, that is the lecture 4, double sideband suppressed carrier, okay. Here we again amplitude modulation we have discussed, limitation discussed. Now before going to the double sideband suppressed carrier, we will go to amplitude demodulation, that is the envelope detector, okay. Then this is the circuit of the envelope detector which will be used to demodulate the AM signal ST. In that ST, it's suppose this is the ST, okay. This is the amplitude modulated signal. Then in envelope detector we have to detect its envelope only, and at the envelope we are having its modulating signal MT. Then using this circuit we can get output empty at the output. Okay. Here we can see, suppose this is ST is input, then it is the diode, okay, along with the resistance RF that is very low. Then because this RFC very low in comparison to its frequency, that is the, then it is charged rapidly and get the output here. Okay. And then these are the condition for the envelope detection, okay, because forward resistance of the diode as well as series resistance multiplied, then this should be less than 1 upon Fc. Okay. And other condition, that is discharging condition, then this RLC, that is the load into capacitance, this should vary between 1 upon Fc to 1 upon W. 1 upon Fc basically the sampling that is the carrier frequencies corresponding to the time, that is the Tc, that is the 1 upon Fc, and this is the time corresponding to the maximum frequency component, then 1 upon W. Then RLC should lies between this to this, so that it can be demodulate the envelope, okay, of the carrier signal. Now, waveform of the envelope detector, okay, that we can see that firstly it is half wave rectified, okay, and then using the RC circuit, that is the low pass filter, we will get this detected envelope at the output, and which is nothing but the close to the modulating signal MT. Okay. And these things, linear modulation schemes and others, and then double sideband suppressed carrier also, that we can discuss in the next, but we can just see linear modulation scheme, because amplitude modulation whatever discussing in the last, that was the non-linear modulation. We can make ST as a in phase component as well as the quadrature phase component, when its part S1t multiplied with the cos 2 pi FCT and SQT multiplied with the sin 2 pi FCT, then ST can be generated in this way. Okay. Here to improve the amplitude modulation, there is a double sideband suppressed carrier. We are transmitting amplitude modulation with the double sideband, but suppressing the carrier, then this is one method. Other is the single sideband modulation, then we are using either lower side or upper side, then it becomes the single sideband modulation. Vestigial sideband modulation, basically we are using either side and along with the vestige of the other side also, some part of the other side also, then vestigial sideband modulation. These we will discuss in next in detail. Then next we will discuss DSB SC in the next class. Thank you very much.